In this lesson, we're going to simplify roots, which means square roots, cube roots, or fourth roots, and that's why we call it nth roots. So we're going to state the vocabulary as well as simplify using factor trees. So let's start by taking a look at some different numbers that we have. First, we have irrational numbers versus rational numbers. With the irrational numbers, we have a number that cannot be written as a fraction. They are non-repeating decimals, and these could also be roots when the radicand is not a perfect square. Let me give you one of the most popular numbers that's irrational that we see is pi. Some of you may have had to memorize some of the digits of pi. When the radicand is not a perfect square, we also have an irrational number. For example, the square root of 3, if you were to punch that in your calculator, you would see that it is a decimal that doesn't repeat and it does not end. We also have our rational numbers, and rational numbers are numbers that can be written as fractions. All of these are decimals that repeat or terminate, which means end. They are integers or roots when the radicand is a perfect square. For example, we might have a fraction 1/2, a decimal point 25. Integers could be -5, 0, 1000, or perfect square. For example, the square root of 4. You've known from a previous course that the square root of 4 could be or is 2. So, let's review. 6 squared, that means 6 to the second power, 36. 6 times 6. -14 squared, that means we're taking -14 times itself twice, and -14 times -14, a negative times a negative is a positive, and 14 times 14 is 196. Now the difference between a problem like number 2 and number 3 is that number 2 has parentheses around the negative sign. In number 3 it does not. So when you have a negative times 9 squared, that means -1 times 9 squared, which is 9 times 9. 9 times 9 is 81, and then times -1 would be -81. What reverses squaring a number? Well, when you are squaring a number, you're multiplying it times itself. When you're taking the square root of a number, you are finding out what did I multiply times itself in the first place. So this is called the square root. For example, if I have 4 squared, that is 16. And if I take the square root of 16, I want to know what did I multiply times itself to get that number, which is 4. So when you take the square root of a number that's squared, these are opposite operations, so they cancel each other. So the square root of a square gives you that original number. These are called inverse operations. Let's take a look at some common vocabulary with roots. Radicals, they are referred to as roots, and they tell us what times itself is the index number, and that equals the radicand. So the index is the number that's right here in the little crook of the root. If there isn't a number there, we remember that it's a square root. The number under the radical is called the radicand, and this is the radical symbol, which we often refer to as the root. Let's look at square roots in more detail. So when we take a look at a square root, remember what we're looking at is what number times itself equals the root. In this case, it would be 5 times 5. Or we could say that the square root of 25 could be -5, because a negative times a negative is a positive. So the square root of 25 could be 5, or it could be negative 5. And as a shortcut, we can write that with the positive negative symbol, so that could be plus or minus 5. The only square root that does not have two answers is the square root of 0, which is 0. Now the other thing we need to talk about is if I were to take the square root of a negative number. Let's say I'm going to take the square root of negative 4. So to answer that question, we want to know what two numbers times themselves will give us negative 4. Well, that isn't possible because I would have to take a negative 2 times a positive 2 to get negative 4. And these are two different numbers, so it's not a number times itself. They're not the same. So when I take the square root of a negative number such as negative 4, there would be no real solution. In other words, when we're dealing with the real numbers, there isn't an answer for that one. And we often can put no solution. We have to understand there's no solution in the real number system. So here are the three basic rules for radicals. There are no perfect squares to be left under the radicand. There should be no radicals in the denominator. And there should be no fractions or decimals under the square root. Let's do some examples. So we're going to simplify these, and we're going to use the factor tree method. So here's what we do. We're going to take and create a factor tree for 90, which would be 9 times 10, 3 times 3. And if you remember what our job is to get our factors to be prime numbers. So 9 is 3 times 3, and then 10 is 2 times 5. So here's what we do. We rewrite the radical in pairs. 3 to the second power, and then 2 and 5 don't have partners. Now what we just talked about on the previous slide was that a square and a square root cancel each other. Or think of it this way. 3 squared is 9, and the square root of 9 is 3. So we're back to where we began. They're inverse operations. So that brings the 3 outside. Or we can talk about the radical jail and say that if you have a partner, you're able to come out of jail. But the 2 and the 5 do not have any partners, and so they need to stay under the radical, and we see that we are multiplying the 2 together. So our simplified version of the square root of 90 is 3 square roots of 10. Let's do the same thing with 192. Let's make a factor tree. So we know that 2 goes into 192, and 2 goes into 192. It'll be 2 times 96. And then 96 we know is 2 times 48. And then if you want to break that into 2 again, or we could go 6 times 8. And 6 we can break down into 2 times 3, 4 times 2, and then we can break our 4 into 2 times 2. So I would like to rewrite my radical with my factor pairs underneath. So I have a 2 and another 2, so that's one pair, so I have 2 squared. I have another pair, a 2 and a 2, so that's 2 squared. I have another pair, 2 squared, and I have a 3. So I know that a square and a square root are opposite operations, so they cancel each other. Or we can use our analogy of the square root jail. If you have a partner, you can get out of jail. So we have a 2 that gets to come out, another 2, and another 2. And what stays under the radical is a 3. Notice that this was all multiplication, so when they came out of the radical, it stayed multiplication. So to simplify, 2 times 2 is 4, times 2 is 8, so we have 8 square roots of 3. Let's simplify these expressions. So we have the square root of 75. So we know that 5 goes into 75, and it goes in there 15 times, so we have 5 times 15, and then we have 5 times 3. Rewriting our radical, with our factor pairs, we have 5 squared times 3. A square and a square root are opposite operations, so we know that the 5 comes out and the 3 needs to stay under the radical. Simplifying the square root of 125, we know 5 can go into here 25 times, and then we have 25, the two factors will be 5 times 5. So when we rewrite our radical with factor pairs, we have 5 squared times 5. A square root and a square are opposite operations, so we know that they cancel each other, and so we have 5, and the 5 stays under the radical. So we have 5 square roots of 5. Now we can also simplify expressions that have variables. So first we have the square root of 16. We know that the square root of 16 is 4, but if you don't remember, we can break that down into 8 times 2, 4 times 2, and 2 times 2. And then what we want to do is we want to break down our a to the third power. We know that that means it's a times itself 3 times. So we want to rewrite our radical with our factor pairs. So we have 2 squared and 2 squared. We have an a squared and an a. Both of the 2's can come out, as well as one of the a's, and the other a needs to stay under the radical. 2 times 2 is 4, so we have 4a and then the square root of a. Again, right away, if you knew that the square root of 16 was 4, we could not have to do the factor tree and simply know that a squared and a would be under the radical, so we could bring the a outside and leave the other a underneath. So let's rewrite this with our factor pairs. We have an x squared, and that what we want to do now is separate all 5 of these y's into pairs. So we have a y squared, and a y. Now, a square root and a square are opposite operations, so we can bring out an x and 2 of the y's, and one of the y's must stay under the radical. So we have x and we have y squared, and that other y stays under the radical symbol. Now we're going to be talking about nth roots. Nth roots simply mean that we have a different index. So if we want a third root, that would be written like this. And what that means is we want to know what number times itself 3 times is going to give us that number. For example, let's say I have 2 times 2 times 2. That's 8. So the cube root of 8 is what number did I have to multiply times itself 3 times. When you make the factor tree, you're now looking for groups of 3 instead of 2 to rewrite our radical. So we have the cube root of 3, the cube root of 2 to the third power. We're going to write these in triples. And a cube root and cubing something are opposite operations, so my answer would be 2. We also have fourth roots, and that's going to be the same concept. What times itself 4 times is going to give me our answer. And so this time we want groups of 4 when we are rewriting our radical. Let's take a look. So for example, we have the cube root of 80. So we want to make a factor tree for 80. So 8 times 10 would work. And then we have 4 times 2 for 8 and 2 times 2 for 4. And then we have 5 times 2 for 10. So we want to rewrite our radical, our cube root, in triples, groups of 3. So notice I have 3 2's, so that's going to be 2 to the third power. And then we have a 5 and a 2. A cube root and a cube are opposite operations, so the 2 can come out. And then, this should be a 2. We're going to leave our cube root, make sure that 3 fits right into the crook right there so it doesn't look like an exponent of the 2. And we take 5 times 2, which is 10. Let's do this one. We have 81, so we're going to break that down into 9 times 9. and 3 times 3 for each of those. Now we're going to rewrite our radical as the cube root, and we're going to write underneath everything in triples. So we have 3 3's, that's going to be 3 cubed, and then we have a 3 by itself. I want to rewrite my p's in groups of 3. Since there's 5 of them, I'm going to have one group of 3 and one group of 2, and then I have a q to the third power. So to simplify, a cube and a cube root are opposite operations, so the 3 can come out, the p can come out, and the q can come out. Then I have my third root of what's left inside would be 3 and p squared. Let's take a look at some fourth roots. So I have 64. I'm going to break that into 8 times 8. I'll break that into 4 times 2 and 2 times 2. And again 4 times 2 and 2 times 2. So when I rewrite my fourth root, I want to put all of mine in groups of 4. So I have 1, 2, 3, 4 2's, so that's going to be 2 to the fourth power. And I have 2 2's left, so that's going to be 2 to the second. So the fourth root and the fourth power are opposite operations, so the 2 can come out, but we still have some underneath that can't be simplified, so I have my fourth root, 2 squared, 2 times 2 is 4. Now I have 324 m to the 6th, n to the 5th, p to the 12th, and we want the fourth root. So we're going to break this down into groups. This is going to be 4 times 81, and then this one's going to be 2 times 2, and 9 times 9, and 3 times 3, and 3 times 3. So I'm going to rewrite my radical, my fourth root, with my groups of 4. So I have 4 3's, that's going to be 3 to the fourth power, and I just have 2 2's, that's going to be 2 squared. My m to the 6th, I want groups of 4, so I'm going to break that down into m to the 4th and m to the 2nd. My n's, I have n to the 5th, so I'm going to break that down into n to the 4th and n to the 1st. And then my p's, I have p to the 12th, so I can break that down into 3 groups of 4. So now to simplify, the 3 can come out, they're opposite operations, the m can come out, the n can come out, and all 3 p's can come out. What's going to be left under my radical is going to be 2 2's, which is 2 squared is 4, 2 m's, m squared, and 1 n. And then I'd like to finish simplifying 3m n p to the third, and then I have my fourth root, and make sure that 4 is right in the crook, and 4 m squared n. So let's review. Rational versus irrational. Remember that rational numbers can be written as fractions, repeating or terminating decimals, and they are integers. Irrational are non-repeating, non-terminating decimals, such as pi or the square root of 2. Square roots, make sure that when we are finding the square root and simplifying, that we are using a factor tree and finding factor pairs. Be sure that your answer is in simplest radical form, that there are no perfect squares left under the radical, that there are no radicals in the denominator, and we don't have any fractions under the root symbol. And also make sure you remember with nth roots that if we're doing third or fourth roots, that we're working in groups of 3 or 4. Please remember to complete the reflection.